All right, everyone, welcome. So, up until now, in our power electronics courses, we've mostly lived in a perfect world, right? Clean components, ideal signals, everything neat and tidy. Well, today we're officially leaving that world behind. We're stepping into the real world, where signals get messy, complicated, and honestly, a whole lot more interesting. I want you to think about this for a second. Those beautiful, smooth sine waves from your intro classes? Yeah, you're pretty much never going to see those coming out of a modern power converter. What you will see are signals that are chopped up, pulsed, and have all sorts of weird shapes. And that brings up a really big question for any engineer. If it's not a simple sine wave, how in the world do you measure its actual energy? How can you predict how hot a resistor or transistor is going to get? So to figure that out, we're going to follow this game plan. First, we'll get familiar with the single most important tool for this job, the root mean square, or RMS value. Then we'll go on a little tour of the common waveforms you'll actually run into. After that, we'll talk about why your job as an engineer doesn't stop at the schematic. And finally, we'll see how it all comes together in a complete system. Sound good? Let's get started. Okay, first up, let's talk about a concept that's going to be your absolute best friend when you're dealing with these real-world signals. It's called the root mean square value, or RMS. Now, this isn't just some random math term. It is the fundamental tool for understanding the true effective power of any electrical signal, no matter what it looks like. So what exactly is it? Well, here's the simple way to think about it. The RMS value is the equivalent DC value that would create the exact same amount of heat. It's the heating effect value. So if you have some bizarre-looking AC current with an RMS value of, say, 5 amps, it means it's going to make a resistor just as hot as a steady 5-amp DC current would. It's an incredibly useful way to compare apples and oranges, or, sine waves and rectangular pulses. And the name itself actually tells you how to calculate it. You literally follow the name, but backwards. First, you take your signal and you square it. See how that makes everything positive? Then, you find the mean, or the average of that squared signal. And finally, you take the square root of that number. Root, mean, square. See? That mathematical process is the engine that gives us that one powerful number that tells us the true heating effect. Okay, so now that we have the concept of RMS in our tool belt, we can start building a sort of practical field guide. We're going to start decoding the language of the signals you'll actually find inside switching converters, motor drives, and all kinds of power supplies. Now, take a look at this. This figure should basically become your new best friend. Seriously, it's like a cheat sheet for power electronics. It's a whole gallery of the most common waveforms you're going to see, along with the formulas you need to find their RMS value. Let's break down a couple of these to see how the shape really changes the energy it carries. Over on the left, that's the classic full-wave rectified sine wave. You've probably seen it 1,000 times. Its RMS value is just its peak divided by the square root of 2. Easy enough. But look to the right. This is what happens when you start pulsing that wave, turning it on and off. Notice that little K? That's the duty cycle, basically the fraction of time that the signal is on. See how it gets right inside that square root? This shows you perfectly that the less time the signal is on, the lower its RMS value, and the less heat it's going to produce. Let's look at 2 more. On the left, you've got a phase-controlled waveform. Think of a simple light dimmer. That's what's happening here. The math gets a bit messier, but the idea is the same. But the one on the right? The rectangular pulse. This is the absolute workhorse of digital power electronics, and its RMS formula is beautifully simple. Just the peak value times the square root of the duty cycle. You'll see this one everywhere. And finally, let's look at signals with ramps, like trapezoids and triangles. Now, why would you care about a triangle wave? Well, this is often what the current looks like flowing through an inductor in a switching converter. And you'll notice, their formulas are different again. See that factor of 3 that pops up? The point is, every single shape has its own unique mathematical fingerprint that tells you its true effective power. So we've gotten really good at analyzing what's happening inside the circuit, but now it's time to zoom out. A truly good engineer understands that their design doesn't just exist on a piece of paper or in a simulation. It exists in the physical world, and you have to think about that. We call these peripheral effects. I know this diagram looks a little weird. You're probably thinking, why is there a floor tile in my power electronics diagram? Well, that's the entire point. It's there to remind us that our circuits make noise. They vibrate. Those sharp, high-frequency square waves we just analyzed can physically vibrate components and create an audible buzz or hum. And all that heat we calculated using RMS, it has to go somewhere, or things will literally melt. These effects, the mechanical, the thermal, the acoustic, they're just as important as getting the electronics right. Okay, For this last section, let's put all the pieces together. We've talked about the messy waveforms and the physical effects they cause. Now, let's see where they actually live inside a complete power conversion system. This right here is the basic blueprint for almost any power converter. You've got your power source and you've got your load. That block in the middle of the power converter, that's the noisy engine room. That's the part that's creating all those rectangular and triangular waveforms we just spent all that time analyzing. So what about those other two blocks, the filters? Well, their entire job is to be the cleanup crew. They take all that messy stuff from the converter and smooth it out so the source and the load see a much nicer, cleaner signal. Now, let's get a little more realistic. This diagram shows you the full picture. You've still got the main power circuit, but look at everything else supporting it. You have the controller. That's the brain of the operation, telling the switches what to do. You have the gate drivers. They're the muscles that provide the oomph to turn the power devices on and off really fast. And then you have isolation, feedback, all the stuff that keeps it safe and stable. It all has to work together. So the real takeaway here is that a power electronic system is, well, it's an ecosystem. The power converter is at the heart, sure, but it's being directed by the brains, the control circuits, and activated by the muscles, the gate drivers. To handle the messy consequences of all that switching, you absolutely need filters. And to keep the whole thing running safely and reliably, you need isolation and feedback loops. Understanding how all these pieces play together is what separates good design from bad. Let's wrap it all up. If there is one single thing you take away today, I want it to be this. The jump from being a student to being a practicing engineer is all about this idea. It's about mastering the messy, non-ideal reality of the signals inside your circuit, and at the same time, never ever forgetting to account for the physical effects your circuit has on the world outside of it. So I'll leave you with this question to think about. We focused a lot today on the heating effect because RMS is so good at calculating it. But what else is there? On your next design project, I want you to ask yourself, what are the unseen consequences of my design? Is it going to radiate electromagnetic noise and interfere with a radio? Is it going to make an annoying buzzing sound? Is it going to vibrate? Because thinking about those questions, that's where the real engineering begins. Thanks for your attention.